I would also like to thank all the organizers, David, Lucrezia, Peter, Lionel, and also to the scientific committee. I really appreciate that I was allowed to present my work here in this beautiful conference. It's the second time I come here. The first time it was in 2017. Well, the second time was the famous pandemic edition, but I was not here in person at that time. Okay. Actually, my presentation is very much related to what we have seen in the morning, especially the talks by Laura and Yehuda Pinchover. And we deal with the p-Laplace operator, the famous p-Laplace operator, which is formally defined in this divergence form. Is except for the case p equal to, this is a nonlinear operator for p greater than 1. And it comes with L2 quadratic form, which is given by this, say, LP norm of the gradient, well, fp to the power p. Okay, and we want, the aim of my talk is to concentrate not really on the p-Laplacian, but on the p-Laplacian in the magnetic framework. And we will see. But first I apologize that I'm going to repeat several facts that were already introduced in the morning, but for the sake of clarity of my presentation, I think it's useful to go through them. So the minus p-Laplacian is a non-negative operator because the associated quadratic form is non-negative. And we say that it's a subcritical operator if it satisfies a Hardy type inequality. That is, there exists a locally integrable function, non-negative v, which is this potential v, and non-trivial, so that the quadratic form is bounded from below by this quantity. So subcriticality means that we still have something in between here. Okay, otherwise we call the operator critical. So the criticality means that 0 is the sharp bound, the sharp below bound, and subcriticality means that this is not sharp, so that we can add something in between. So the question is, the p-Laplace operator is critical or not? Well, the answer to this question is related to the celebrated Hardy inequality in the LP setting, which holds for P between 1 and D. This is the dimension, the Euclidean dimension. And it asserts that if U is in W1P, then 1 over modulus of X belongs to LP also, although there is a singularity which appears here at the origin. In addition, they are comparable, these two quantities are comparable with this constant, which is sharp. And the inequality here is not achieved. Actually, the inequality is strict. But the constant is optimal. Okay. Okay, sorry. And the Hardy inequality tells what? Well, tells that the minus p-Laplacian is subcritical when p is less than the dimension constant, because can be bounded from below by such term with v being exactly the Hardy potential. Okay. On the contrary, when p is greater than a dimension, the p-Laplacian is a critical operator. And this is, I apologize because I didn't put any reference here, but Yehuda Pinchover explained this fact in many of his papers. So the fact that there is no Hardy weight where p is greater than t for the p-Laplacian. The only Hardy weight is the trivial one. Okay. Well, now we are legitimate to do what? In the case when p is less than dimension, we can subtract from the p-Laplacian this Hardy term. We still get a non-negative operator, and we wonder if this is still critical or not. So, and the answer is that it's still critical. So this constant here for this Hardy operator, Hardy type operator, is optimal. So this inequality cannot be improved when p is less than the dimension. Okay, now what about the magnetic p-Laplacian? Well, the magnetic p-Laplacian is defined by this formula 6 in terms of the magnetic divergence and the gradient, magnetic gradient, which are defined as, in this way, as magnetic perturbations of the standard gradient and divergence, respectively. Here, A is a so-called magnetic potential defined from Rd to Rd, so it's a vector. It could be interpreted as a one differential form. And once we have this operator, of course, when A is equal to 0, we recover the classical p-Laplacian, the free magnetic case. We also have an associated quadratic form for this magnetic p-Laplacian, which is described very similar to the p-Laplacian. But instead of the gradient, we have the magnetic gradient here. Okay, and we try, and exactly in the same way, we can extend the notion, the definition for the criticality and subcriticality for these operators. Okay, just a few words about this. So from the physical point of view, the more important quantity is the so-called magnetic field. So this B, this is related with quantum mechanics, with the motion of charged particles, and in electric and magnetic field. So this is the magnetic field. It's basically a two-dimensional differential form or a matrix tensor, which satisfies the Maxwell equation. And the relation of B with A is given by this formula. So B is just the exterior derivative of A, or more precisely, the components of this matrix tensor B are given by this difference between the cross partial derivatives of the magnetic potential A. So this is the mathematical formulation. From the physical point of view, B is the quantity that that really matters. B is unique. So for a unique B, we may have various magnetic potential A satisfying this equation. So the choice of A does not matter too much, because as I'm saying here, if you take 2a satisfying this equation, then this means that a minus a tilde is exact, but since it is exact in the Euclidean space Rd, it is also no, it's closed. So it's closed, and then since we are in Rd, it is also exact. So it's a gradient of a zero form. This is a scalar function. And due to this fact, we'll see that the domain of these quadratic forms associated to two different a's is the same, and basically also the quadratic forms are equivalent up to some transformation. So from our point of view, it does not matter which a we take into consideration. Okay. We also have the diamagnetic inequality, which tells that you can control pointwise once you have a, say, a function u smooth enough, well, in the domain of this operator. The magnetic gradient controls the gradient of the modulus of u, and as a consequence of this, of course, we have this trivial inequality. So what I want to say is that all the inequalities that we obtain for the p-Laplace operator, not for the p-Laplace, but for the quadratic form associated with the p-Laplace operator, can be transferred to the case of the magnetic operator. The question is whether we can get something more because of this, because of having this magnetic field. So we expect that the magnetic field to influence our inequalities and to obtain improvements in our inequalities. Okay, so this is the first result. Take P greater than the dimension. B is a smooth and closed magnetic field, and A is such that this is a magnetic potential satisfying that A is equal to B. Then we have this inequality with a uniformal constant here, uniform constant in U. This does not depend on U. And the weight here that we get is precisely this has this expression. So, sorry. When P was greater than D, the p-Laplacian was critical. So this theorem says that when we add magnetic field, non-trivial magnetic field, we get that the magnetic p-Laplacian is subcritical because we get a non-trivial quantity here. So what's the novelty of this result with respect with what has been done so far in the literature? Well, first of all is that we extend the analysis to the LP setting. And maybe with the same importance is the fact that this potential is unbounded at the origin. So you see, when P is equal D, this x to the power P minus D is 1. So the log term, when, for instance, when x goes to 0, this is large, this goes to infinity, so this dominates this term. So basically, the behavior of the potential is given by this part as x goes to 0. And this is this blows up. It's unbounded potential. And actually, we didn't prove in the paper, but it is sharp. We cannot have a better behavior at the origin. Okay, at infinity, the term that wins is this one. okay, especially when P is greater than D. So the potential V rho behaves like 1 over x to the power P as x goes to infinity, as x goes to infinity. So this formula encodes both at the behavior at 0 at infinity. Okay. So this is the remark. So previously we proved this, but in the case P equal 2 and D equal 2, for instance, this potential in our case in the first paper was bounded. Okay, then it can be improved under some additional conditions, so you can remove this log term so to get a better weight. And more recently, if you impose also the magnetic field to have be compactly supported, then you get a non-bounded weight rho. In the case of Harlow-Bond type magnetic fields, well, this is not the case which fits to our analysis because this is an unbounded magnetic field. But anyway, since it is unbounded, you expect to get a new constant in the hard inequality, and this is what was done by Laptev and Weidel. So they got a singular potential at the origin, but because they worked with a singular magnetic field. So far we have worked with smooth magnetic fields. Okay, so this is what I said. So in this case, we extend basically, we remove all these conditions here and compactly supported, not needed, this condition, this Fox condition, not needed. And we also extend the analysis to the LP case with an unbounded, sharp unbounded potential. Okay, this is the sketch of the proof, but how much time do I have more?
8 minutes.
8? Okay. Well, the sketch of the proof, so this deals with, it has 3 parts. A Hardy type inequality near the origin, Hardy type inequality at infinity, and some analysis on an annulus, okay? The magnetic potential does not enter into the subject except in the middle. So we don't need the properties of the magnetic field at 0 at infinity. We just need the properties of the magnetic field of an annulus, but there, since things are bounded, we are able to show that this Rayleigh quotient, when you take the infimum of this Rayleigh quotient, you get a strict positive quantity here when you take that. Okay, this is well defined in W1P because A is bounded. You have compactness, the infimum is achieved. If you assume that the infimum is 0, then you will get that A must be an exact form, but A being an exact form will imply that dB is equal to 0, so it will imply that the fact that B is equal to 0, which contradicts our assumption. So basically, when gluing these 3 pieces with a localization argument, we get this result. Okay. So now this was for the p-Laplacian, but magnetic p-Laplacian. Now subtract. Consider this Hardy type operator for in the magnetic case. So we know that this is non-negative for any A, including A equals 0, which is the case of the free magnetic case. Well, a preliminary result is the following. So we are able to build the quadratic form of this operator in terms of this gradient, magnetic gradient term, which is positive. So we know that this is positive. We wanted to find a precise quantity to say that. Well, we get here a constant. Unfortunately, well, the constant is explicit, but it's not a good constant because it does not depend on the magnetic field, which is what you would expect to get in order to get sharp results. And moreover, this constant, when you take the infimum of this algebra, well, this term, will be 0 when p is less than 2. So when p is less than 2, this inequality does not tell you anything. So that's why the case p between 1 and 2, we are not able to treat it, and this remains open. So with this intermediate, say, Hardy type inequality, well, the key proof in this inequality is the fact that you see this term here, which is a priori is a very annoying nonlinear term, depending on the magnetic gradient, actually is not depending on the magnetic gradient. There is a cancellation phenomena with the magnetic gradient here. So you can remove the magnetic gradient for this, and you get exactly the free magnetic case. So using this property, we are able to prove the previous inequality, where this expression C of P, this expression C of P is given by this. Okay, it's a number in. Okay. Okay, and this is the result, similar as in the case for the p-Laplacian. When adding magnetic field and subtracting a Hardy potential, we get a subcritical operator when p is less than 2. The weight here is this. The weight behaves when x goes to 0 as, you see, this one seems useless here because the log dominates 1 both at 0 at infinity. But, I mean, does not matter too much, this one. It's just to be sure that this is not vanishing on the unit sphere. Okay, so this row here gives me the behavior at 0 at infinity. In the middle, the behavior, it's a constant. I mean, it's bounded. The weight is bounded. But if you remove 1 here, you will not get a bounded. This blows up on the unit sphere, and this is not allowed because this term will not be integrable. I mean, this will force you to vanish on the unit sphere, but since unit sphere is n1 minus 1 dimension, d minus 1 dimensional, you cannot see infinity functions with compact support except the unit sphere are not dense in the domain of the operator. So that's why this is just for simplicity. Okay. Now we also consider the case of Harron-Bohm potentials. So this actually goes back to the paper by Lapte-Weidel that I mentioned before. So what you know that in 2 dimensions, the Laplace operator is a critical operator. The Laplace operator, and but when you consider, for instance, Harron-Bohm potentials, and you get an improvement. I mean, you get the Hardy inequality in 2 dimensions. The best constants here, when p is equal to, is the distance from this beta to the, well, actually, no, you get a non-trivial inequality when this beta is not an integer, okay? Because the best constant will be given by this, the distance from beta to the integers square. And, okay, this is in 2 dimensions and for p equal 2. now we stay with the dimension 2 and we ask for p less than 2. So for p less than 2, this is integrable. And what we succeeded to prove is that we also get an improvement of the best constant with respect to the best constant of the Hardy inequality when we are with a free magnetic case. So, but the problem is that we don't have a control for this constant. The constant that our constant is related to this minimization problem, which is very easy to be computed when p is equal to, but when p is less than 2, we are not able so far to determine explicitly how much is this constant. So this is also an open problem. Although we get an improvement in inequality, we don't have a control for this improvement. Okay. Thank you.
Are there any questions for the speaker? Please.
Let me just mention that there is a nice paper, short paper by Cyril Tintareff. At that time he was Kirill Tintareff, okay. But saying that if you have a non-negative potential, I mean a quadratic form, then if you add any magnetic field, then it becomes subcritical. And I must say that I read it many years ago, and then quite recently we discussed it with Hine Kovacic and Gabriele Grillo, and we wrote a proof, and then I reminded that he proved it already. So the proof is by the ground state transformation.
So this is in L2 setting or LP setting?
LP, NEP, NEP. You said that you know how to do it for P greater than D, yes, or something like this, but it's for NEP. So you start with non-negative quadratic form or form, and then you add magnetic potential, you get subcritical operator.
Okay,
actually, if you go back, it is in your go back. No, I think it's you had you wrote something that you kill the magnetic field.
Ah, okay, yeah, here, this term, I, sorry. So yes, this quantity, if you look to this quantity, this
is a ground state. D to x to the d minus p divided by p is a ground state for the Hardy potential.
Yeah,
in general,
this,
you take
yes, this is a ground state.
If you are in the critical case, you do the ground state transform with the ground state.
With the ground state of the Laplacian.
Then you get a Hardy weight. And this is general. It's not just this Hardy classical Hardy weight.
Okay. Thank you. Well, we will discuss after.
In the interest of time, let me suggest that other questions might be directed to Professor Cazacu directly. So let's take the speaker again.